Our next presenter is Sadia Nourin. She will be talking about detecting network interference without endpoint participation.
Hi everyone, my name is Sadia, and today I'm going to be talking about how me and my co-authors are building a system that can detect network interference without endpoint participation. So many authoritarian regimes enact nation-state censorship, threatening the free and open communication on the internet. And this means that people inside of these censoring countries will try to access a censored web page and will end up either getting a government block page, getting their connection terminated, getting their connection throttled, or getting all of their traffic dropped completely. In an effort to combat and understand such censorship, it's important to conduct censorship measurements in order to answer questions such as what exactly is being censored, what domains are being censored, how censors operate, and how censorship changes over time. Currently, there are two primary ways that we use in order to measure censorship within the research community. And the first one involves recruiting volunteers from censoring nations to run censorship measurement software on their own personal devices. This comes at their own risk as well. And UNI, or the Open Observatory of Network Interference, is one such platform that conducts measurements this way, and they've been doing this for more than a decade and have been quite successful as well. The second approach is to obtain remote machines within the censoring country. This could be vantage points, public servers, or VPN servers as well. And Censor Planet is one such platform that obtains public servers in order to do their measurements. And IC Lab is also another platform that uses VPN servers. And again, both of these techniques have been successful. And volunteers on remote machines in general work great in most countries. They've been used to study powerful nation-state actors like China, Iran, and Russia. However, there is this long tail of smaller countries where these techniques don't work as well for, and these countries are often characterized as having small populations, extremely repressive regimes, which makes it difficult to get volunteers, low internet penetration rates, as well as poor internet infrastructure. As a result, even when censorship is possible at times, it usually only gives us a glimpse of censorship at a single point in time. And this is often followed by periods of low or no measurement afterwards. And sometimes they can only test a handful of domains as well. So we seek to build a new censorship measurement system that can longitudinally test millions of domains without the need for any volunteers, vantage points, or endpoint participation within the country. And we want to emphasize that this is meant to complement, not replace existing efforts, by giving insight into hard-to-reach networks or networks that are not reachable at all by current efforts. So I'm going to go into the background of how we seek to build such a system, give a high-level design overview, and then finish up with some preliminary results that we found. So the key idea behind our censorship measurement system is going to be the fact that a lot of censoring middle boxes do not fully adhere to the TCP protocol and are therefore TCP non-compliant. So specifically, we're going to focus on HTTP censorship, but this also applies to HTTPS as well. So in this example, usually a client will send a TCP three-way handshake with a live server, and then subsequently send a censored request in the form of a push ACK. Usually when censorship happens this way, the censor is going to, of course, detect the push ACK and then send a blocking response back to the client. Here it's a reset. It could also be a block page or so. However, censoring middle boxes can expect to miss packets from time to time, and this can be due to high traffic, load balancing, or asymmetric routes. So let's assume that the client has sent the TCP three-way handshake, but the ACK maybe went in a different route, and the censoring middle box has missed the ACK. The client subsequently sends the push ACK with the censored request, and we would expect the censor to disregard this push ACK because from its perspective, there is no ongoing connection. However, the censor actually still sends a reset back to the client, therefore terminating the connection. And this just shows us that censoring middle boxes just need to have the presumption, not the actual confirmation, of an ongoing connection between a client and a server in order to take blocking action. Now, this is actually great for us, though, because we can replace that server with a non-responsive IP address and then send a packet sequence, which is enough to trigger the censor to take blocking action. So in this example, we just send a SYN and follow that up with a push ACK in order to trigger the censor. So this technique has actually been used in previous work before in the form of triggering censors for TCP amplification attacks. The SYN followed by the push packet sequence that I showed you all was discovered by Bot et al. And along with other packet sequences as well. So the SYN push packet sequence strategy is not the only attack, and it's not going to work for every single country. And we subsequently used the same technique as well to measure censorship in Turkmenistan. We tried using all of the packet sequences that Bach et al. Discovered in their previous work. However, none of them were able to trigger censorship in Turkmenistan. So we pivoted to manually determining the packet sequence. And we discovered an odd packet sequence here where we send a push ACK, follow that up with a sleep from 5 to 29 seconds, and then the same push ACK again. And that's enough to trigger censorship in Turkmenistan. But this just goes to show that there's all this bizarre, undocumented behaviors by censoring middle boxes that we really just need to understand and determine before we try to trigger the censors without any endpoint participation. And unfortunately, manually determining all of this is not going to work. It's not going to scale for other countries, and it's also not even going to scale for countries that have ISPs implementing decentralized censorship. And so we turned to Geneva to automate this process. And Geneva is an open source genetic algorithm that trains against live sensors to discover packet sequences that evade censorship. However, we're actually going to modify Geneva so that instead of evading censorship, it triggers censorship, and all we need to do is change the fitness function for the genetic algorithm for this. For the extended abstract, we focused on HTTP censorship. However, our generic approach is extendable for HTTPS as well, and we hope to do so in the future. So once we train Geneva and Geneva discovers a packet sequence, we can now trigger censorship on one IP address as Geneva trains on one IP. But this means that we can also trigger censorship on virtually all of the IP addresses within that same AS or network because it's just sending one packet sequence to all of the IPs. So this means that we can not only measure networks that current tools can't access, but that we can hit more endpoints in other networks as well. So you might ask, why does it matter that you can hit more endpoints? Well, in our previous study in Turkmenistan, we discovered that censorship is not uniformly distributed over IP addresses, even within the same /24. So some IP addresses experience censorship while others don't. And so our tool gives the added benefit of identifying how diverse censorship is within an AS or another network. All right, so now I'll go into the high-level design of our system. So a country is eligible for our measurement system if it has the following 3 requirements. The first one is that we need at least one, if not more, confirmed censored domains. Because when we're training Geneva, we need to put the domain within the payload in order to ensure that at least if we do have a successful packet sequence, it will trigger the censor. And so we can get the censored domain from other current measurement platforms that are running. We could also get it from anecdotal information from residents within the country or other reputable sources as well. We also need the country to exhibit bidirectional censorship. And bidirectional censorship is when a censor filters all traffic regardless of whether it originated from inside or outside of the country. So this is great because, again, we can have a machine or a client outside of the censored country and send a request to trigger the censor. So we can determine this information of whether or not a country has bidirectionality by looking at current measurement platforms. So Sensor Planet uses the ECHO protocol, and that essentially is able to trigger bidirectional censorship, so we can use that as a baseline. However, we can also run our own experiments to determine this as well. And I have a short model here. So we can first send an uncensored request to a live server that we connected with, and then obviously the sensor is going to disregard this because it's an uncensored domain. However, the server is going to get back to us normally. We're then going to follow that up with a censored request straight to the server. This time, the sensor is obviously going to pick up on the request and censor it because the domain is a forbidden domain. And now the client essentially has 2 different responses that it received for both of the domains. And assuming that the server does not host any of the content for either of the domains, we really shouldn't have received 2 different responses. So this is essentially telling us that there is bidirectional censorship happening. The next requirement we have is that the country must exhibit little to no residual censorship. And residual censorship is when a censor filters all requests from a client for an extended period of time because the client sent a censored request beforehand. So it essentially put the client's IP address on a block list. And we want to determine this because when we're sending out our measurement probes, there may be possibility of false positives happening because an uncensored request is uncensored domain is subjected to residual censorship. So first, we're going to, in order to determine this, we're going to send a censored request first this time. And of course, as last time, the censor is going to send a blocking response back to us. And then we're going to follow that up with this uncensored request. And this time, we should, if the country deploys residual censorship, we should expect to get the same censored response back if the censor actually deploys residual censorship by sending a response. There's also other types of residual censorship where the censor will drop all your traffic. So what's important to do afterwards is to compare the response we received, if any, for the uncensored request with what a normal uncensored request would look like. And of course, if there's a difference, then there's residual censorship here, and we might have to evade it during our measurement probes. And that could just mean waiting for it to expire before sending out our probes, or sometimes changing the port numbers works as well if they implement it at the 3-tuple level of a TCP connection. All right, so once a country meets all the requirements, we can modify Geneva to trigger censorship instead of evade censorship, and then train Geneva on at least one, if not more, non-responsive IP addresses in the country. And this means that if we receive any response at all, it must have come from the censor because, again, we're sending these out to non-responsive or non-live IPs, and that means that Geneva has discovered a successful packet sequence. And so now we can send this packet sequence out with our test domains, which is just a list of domains that we want to check for censorship, to all other non-responsive IPs to conduct measurements. All right, so we tested our censorship detection approach on a few different countries. However, we leave the measurement up to future work. We were able to have it be successful in 2 countries so far, and unfortunately, it was also unsuccessful in some other countries as well. So Brunei was one country where we were able to detect bidirectional censorship in, especially in AS 10094, which covers 70% of the internet, which is mostly their residential population. So we're getting quite a comprehensive view here. And when we trained Geneva on this AS, we discovered that the regular packet sequence I showed from earlier, SYN followed by a pushback, is enough to trigger censorship in this country. And we also discovered that there's no residual censorship, so we don't have to worry about false positives when sending out our measurement probe. The second country is Tajikistan. We detected bidirectional censorship in 24722. However, this AS only covers 11% of the internet users within the country, so it really doesn't give us a wide view of the nation, even if we did censorship within the AS. So it kind of comes back to my previous point in that this needs to be used in conjunction with other platforms in order to gain that comprehensive view we're looking for. When we train Geneva in this AS, Geneva discovers that sending a pushback packet with the payload in it twice, right after the other, is enough to trigger censorship. And previous work has determined that sending it once has triggered censorship in some countries, so this may seem a little bit more redundant. However, this may be also more reflective of typical client browsing behavior, where we send multiple pushback packets in order to fetch multiple resources from an origin to render a full web page. And again, there's no residual censorship in this country, which makes it easier. We don't really have to worry about false positives too much. All right, so we also tried to trigger bidirectional censorship in Burundi, Equatorial Guinea, Kyrgyzstan, and Myanmar. However, we chose these countries because, again, they're small countries, they have low internet penetration, and some of them also have really repressive regimes. But unfortunately, there was no bidirectional censorship that we could detect, and so we didn't even train Geneva on it. And so I just want to close off with the fact that we really do want to use this measurement technique with other systems as well to gain a more comprehensive view of these hard-to-reach networks, or just hit more endpoints within all the networks that are already reachable. But we do have this limitation in that not all countries and networks meet the requirements we set forth. So what we're really trying to understand here is what other challenges are we overlooking when implementing this system at a global scale. That's all for me. Thank you all for listening, and I'll take any questions.
Awesome. To the second, your precise finishing up. We have a couple of questions, but we noticed some of you are not yet connected to Zulip, so we are also okay with you raising your hands, and we give you guys microphones to ask your question from now on. So having said that, we still have questions that I'm going to ask. So how do you ensure your non-responsive IP addresses do not get blocked by censor in the form of collateral damage? And how do you ensure it reflects the view of real clients in the country or residential network in the country?
So usually when we're talking about non-responsive IP addresses, they're within the same AS, and these are non-responsive IP addresses from outside of the country, so they don't have a port open for us, but they may be connected to a machine inside. Usually they are subjected to the same amount of censorship, but yes, there could be differences as well. And what was the first part of the question?
The part was your non-represented IP address do not get blocked by censor in the form of collateral damage.
Collateral damage from outside of a different country, or?
Yeah, so Ram is going to elaborate more.
Sorry, I think my question was, so you're trying to trigger censorship on a non-responsive IP address from outside the country, but like you mentioned, these IP addresses could be connected to clients within the country. And let's say you're triggering the censor to block a domain. How do you ensure that the client from inside the country, when they're trying to access the same domain, it doesn't lead to collateral blocking, right? Because some countries like China implement residual blocking. So the same domain is blocked for, like 120 seconds for the same client or IP address endpoint. But do you factor that in your measurement design?
So when you're speaking of collateral damage, I'm still trying to understand, does that mean that other countries could have, get in within the connection and block that connection as well?
No, I mean, I'm talking about these clients that these IP addresses belong to. They don't know that you're triggering the censorship, right? So they don't really control what you are doing. So is there a possibility that they are blocked from access to some domains by the censor?
Yes, I mean, we can solve that by just spreading out our measurement probes, however. If the maximum duration is 5 minutes, then send out the measurement probe at 5 minutes or change ports as well.
Yeah, I think it'd be a good idea just in general to think about this problem, because you don't want to inadvertently cause any damage to real clients within the country, right? But through the measurements that you're making, since you don't get consent from these IP addresses to conduct measurements to them. At least at this point, if there are sensors that are taking an active interest into the measurements that you're doing, and they're seeing that you're sending all of these measurements to these IP addresses, and then they block those IP addresses from accessing that content in the future, then that might be problematic. So I think it'd be good to think about how you can stop that from happening even before you conduct the measurements.
So our clients are outside of the censored country, though. So even if they do block the IP addresses, it would just be...
Sorry, by clients, I mean the remote endpoints that you're sending them.
Yeah, that would be a problem.
Really quickly, could we have the next speaker start to set up?
Any other questions? Thank you so much. Sadia.